Welcome to Spring LIB.
Okay. In this problem, we have X-rays being produced by a potential difference, and these X-rays are scattering in a Compton effect, Compton scattering, with a scattering angle of 45 degrees. With this information, we're asked for the original wavelength of these X-rays, the new wavelength of the X-rays after Compton scattering, and the energy of these X-rays after Compton scattering. So the primary equation we will be using to solve for all of these quantities is the Compton scattering equation, which relates the change in lambda and wavelength of these X-rays to the angle of scattering. The other small piece of information the other equation we'll need is the energy of light in general, which we can write as E equals hc over lambda. So the energy of light is inversely proportional to its wavelength. We'll be making use of the speed of light and Planck's constant. In this case, I'm using Planck's constant in joules per second, not in electron volts. All right, let's get started. Okay. So to start, we can note that in order for the X-rays to be created, we can assume that all of the energy from the potential difference is converted directly into the energy of the X-rays. So we can say that the total energy of this potential difference, E times V, is equal to the energy of the X-rays, which we can write hc over lambda. Rearranging, we can solve for the initial lambda, which is simply hc over E times the potential difference, V. It is worth noting that this is not electron volts. This is actually the electron charge E times the potential difference V. And this is our resulting lambda. So numerically, we have 6.626 e to the negative 34 joule seconds times 3 e to the 8 meters per second. All of that over the electron charge, 1.6 e to the negative 19 coulombs. And the potential difference that we're given, which in this case is 24 kilovolts, so 24 e to the 3 volts. Okay. So doing that computation, we have our resulting lambda, which is 5.176 e to the negative 11 meters. Okay, so it's about twice a picometer, which is quite large. Okay, so that's our lambda, the initial lambda before scattering. Now, to get the lambda after scattering, we use the Compton scattering equation. We don't actually have to do any algebra because everything will be already in the right form. So we have 1 minus the cosine of the angle, which they give us is 45 degrees. So all I have to do is simplify this down. We can use our original lambda that we just solved for. And this quantity h over mc calculated will end up being 2.46 e to the negative 12. And 1 minus whatever the cosine of 45 is. It's an easy angle. All of this together should turn out 5.2476 e to the negative 11. So 10 to the negative 11 meters. And this is our new lambda prime. So at this point, we can probably box these two answers. Great. So now that we have the post-scattering wavelength, we can easily get the post-scattering energy, call it E prime, as hc over lambda prime And you can simply insert the Planck constant as before, C as before, divide it all over by what we just found for the new wavelength, 5.2476 e to the negative 11 meters. And after crunching those numbers, we will end up with a result of 23675 electron volts. Or I should put it in joules first. I didn't actually do the conversion here. So in joules, it's 3.788 e to the negative 15. Dividing this by 1.6 e to the negative 19, which is the number of joules in an electron volt, we can get our answer in electron volts instead, which will be much nicer. 23.67 keV, kilo electron volts. And that's a reasonable amount. That's a reasonable number for the energy of an X-ray. So there we have it. We were able to, using just simple energy conservation, assuming that the potential difference gives all its energy to the created X-rays, we can find initial lambda. We can use the scattering equation with a known angle to find lambda prime. And from lambda prime, we can easily find the energy of our post-scattered X-ray.